So the previous discussion of Sagittarius representations hopefully whet your appetite for coordinate-independent representations of molecular tensors. But however, those do have a few limitations, and it's nice to have a suite of complementary methods. I'll talk about two. So the first is a unit vector sphere representation, and then the next is hyperellipsoid representations. So again, to remind you, why didn't we like? What were some of the limitations of the Sagittarius representations? They're very convenient for looking at individual resonances concisely and allowing us to fully reconstruct the full set of 27 tensor elements in any arbitrary coordinate system by projection upon the molecular frame. However, they only work for individual transitions. If we want to ask what an ensemble of multiple chromophores is doing in terms of its nonlinear optical properties, the vector sphere representation is not as advantageous. We can look at coupled systems, but that's a whole different topic for another day that you'll be getting soon enough, I'm sure, if you're interested in carrying on. So the first representation, alternative representation I'll be talking about, is the unit vector sphere. And this was originally developed out of Virgus Barsta's group at the University of Toronto, and I think it's one of the most clever approaches for visually representing tensors in a general architecture, be it either for individual transitions or for molecular assemblies. So how do we interpret these vector spheres? Well, imagine let's pick any particular point on the surface. For example, right here. And imagine we're driving this with an electric field oscillating back and forth along this direction from the center of the sphere to that particular point on the surface. The vector on the outside of that sphere indicates the polarization of the nonlinear signal that's generated by that driving polarization. So in this case, blue and pointing away would indicate a coparallel polarization that's positive in phase relative to the driving field. So we developed a software package, NLO Predict, that's built into UCSF Chimera as a tool for aiding in visualization, and it includes the vector sphere representations. So, as I said before, from the center to any point on the surface, the direction and magnitude of that vector indicates the magnitude and sign of the nonlinear tensor. So let me just give you an example. I'm going to take this blue point and just sort of put these blue points driving right toward us. Let's rotate this around too, so it looks a little cleaner. The coordinate system here is the z-axis is out of the screen, x is horizontal, and y is vertical, so according to a right-hand rule. So if I look at this, I should have, in this representation, I should have a really big, all these blue points are, these blue arrows are pointing along the positive z direction, so I should have a big zzz element. And if I look on the y-axis, it should be pretty big as well, but negatively signed, because I have negative lobes here pointing up toward red, and then blue is pointing down toward negative y, so that combination is going to give me a large but negatively valued YYY and a large but positively valued ZZZ. And the x component, XXX, should be essentially zero, because you see the white indicates that there's really zero amplitude. And that's exactly what you see from the set of 27 numbers you get for representing this particular molecular tensor in any arbitrary coordinate system. In this particular coordinate system, XXX is very small, YYY is large and negative, and ZZZ is large and positive. But of course, I can move this around and come up with a set of all 27 numbers in any arbitrary coordinate system, but this vector sphere representation is always remains fixed relative to the molecular frame and has that key advantage. The vector sphere representation is not the only game in town, however. We can also look at alternative visualizations. And if we choose a space-filling representation, then that we call a hyperellipsoid. Basically, it has the same red and blue characteristics in terms of blue being positive in sign and red being negative in sign. What's different from the vector sphere is that we are only considering the coparallel polarized component. In other words, this would be the projection. If we go back to the vector sphere representation, it'll be a little bit easier. All these arrows, if we ask what is the projection along the sphere normal at every position and turn that into a scalar value, then that is the distance away from the origin in the hyperellipsoid. So it's just the hyperellipsoid represents the coparallel polarized component of the vector sphere representation. Of course, the vector sphere contains additional information that is lost in the hyperellipsoid representation, but it's a little bit easier to wrap your mind around what's going on with the hyperellipsoid representation. So each of them has its own pros and cons depending on what you want to do with it. As in the vector sphere representations, the hyperellipsoids can also be used to describe either individual transitions or ensembles of many transitions, because it's not dependent on resonances with a particular transition state. What's shown here, for example, is a hyperellipsoid representation of the collagen structure. If you do a symmetry additive summation of all of the amide contributions in a protein, you can come up with representations for that, along with representations for crystals in different symmetries. However, there are limitations, and I mentioned the fact that you only recovered the co-parallel polarized component of the vector sphere representation. Well, this is one case where the difference is most noted. If you look at, for example, something with D4 symmetry for your point group, and this might be a crystal class like in tetragonal lysozyme, for example, then there's really only one unique non-zero tensor element, and it turns out that no matter what the orientation of the molecular crystal, it can only ever generate cross-polarized output. And in this case, there is no hyperellipsoid representation because there is no projection along the normal to the sphere, and yet there is still second harmonic and some frequency activity as visualizable through the vector sphere representation.